Can you hear me now? Could you write in the channel if you hear me now? Could you write in the channel if you hear me now? Could you write in the channel if you hear me now? Could you write in the channel if you hear me now? Could you write in the channel if you hear me now? Could you write in the channel if you hear me now? My YouTube is not if you hear me now. My YouTube is not if you hear me now. My YouTube is not if you hear me now. Excellent. So I'm glad we've resolved these technical problems. My name is Kurt Batista from the University of Warwick. A very good morning from the United Kingdom, and good afternoon to some of you in Asian countries, and a very good evening for our American colleagues. We have three very exciting presentations this morning, and can I encourage you to post any questions in the Discord? So after the presentations, the Q&A session will be run by questions via the Discord, and I will read out the questions and the presenters will answer. Our very first presentation is entitled Finding Efficient Spatial Distributions for Massively Instanced 3D Models. The authors are Stefan Zellman from Cologne University, Nate Morikal from Utah, Ingo Wall from NVIDIA, and Valero Pascucci from Utah also. So Stefan, if you could present now, please. Should be switching to a video of the presentation shortly, hopefully.
Hi, I'm Stefan, and today I'm giving this talk about finding efficient spatial distributions for massively instanced 3D models. Instancing is a technique that is used to get the memory footprint of large 3D models under control. The basic idea is to store a somewhat complicated mesh only once in memory and then replicate it many times by creating lots of references to it. With each reference, we associate an affine transform so the mesh can be moved into the right position and be oriented accordingly. Of course, in order to not break the illusion, the mesh that is instanced should lend itself to instancing. For example, consider maple leaves that are scattered across the ground. As a pair of individual maple leaves in real life will not look so different, the user will probably buy the illusion that 2 or 3 instances masquerade as a couple hundred of actual maple leaves. Disney's Moana Island scene, for example, contains 1.5 million base meshes and 67 million instances that are associated with the base meshes. All the tiny leaves, bushes, foliage, and twigs lying around on the ground are replicated hundreds and thousands of times using instancing. To get a grasp of the complexity, we here show the geometry colorized by instance ID. Each color indicates a different instance. Instancing reduces the complexity of the model, as when all the instances were flattened out, this scene would have billions of primitives. Still, as datasets grow bigger and bigger, even with this optimization, the user might desire to render such models in parallel and on a distributed system. This model, for example, requires tens of gigabytes of memory, much more than is nowadays available on a single consumer GPU, and also more than you find on most workstations or PCs. Unfortunately, with instances, sensible data distributions are much harder to find than in the absence of instances. In this talk, we'll analyze what the challenges are with instance models and how to find spatial distributions that overcome these challenges. Our approach is based on spatial subdivision with a KD tree. Let us briefly recall what it involves to build a KD tree in a top-down fashion, which is the approach that we have taken. Say we have a couple of objects that we want to partition. Let's for the moment assume that we don't have instances yet, but just a bunch of objects. We would first compute the domain of all the objects, which in the beginning would just be all the objects' bounding box. That is, the bounds of the spatial domain are the same as the object bounds of the union of the objects. Then we sweep a plane through the model's domain and determine a split at a position that we find advantageous. Which split position we prefer, we decide based upon some sort of metric or cost function. There are rather obvious optimizations to this approach. like for example testing only those planes that go through the axis-aligned bounding boxes of each object, or like using binning, which requires us to project the objects to a finite number of bins and then only testing the planes at the bin boundaries. We would then compute the domains of the objects to the left and to the right. Subject to certain halting criteria, we would then recursively process both sides. When we found a split position, the new domain bounds to the left and to the right are determined by clipping the old domain against the split plane. We optimized this a bit further by clipping the domains at the object bounds of the primitives, so we potentially even get bounds that are a bit tighter. Sometimes, like in this example, the split plane would go through one or more objects. Objects that straddle the split plane would need special handling, by either splitting them at the primitive level or by storing copies of them on each side. With instancing, the problem of finding good spatial distributions becomes more involved. Let's discuss that using this slightly modified example. We now have two base meshes with a bunch of instances. The blue and the red guys each belong to one base mesh. Now the first question we have to ask ourselves is if we want to partition the model by instances or by base meshes. Let's say that this is a split we have found. Let's also assume that we partition by instances. We assume in this talk that splitting instances on the primitive level is just not feasible. That is, even if the base meshes are very complex and require lots of memory, we'd have to replicate them on all nodes. If done naively, this can result in massive memory consumption overall and on each compute node. Recall that every node that holds a reference to a base mesh also needs to store that base mesh on local memory. Now, let's assume that we partition by base meshes instead. In this example, the instances belonging to each base mesh are spread out all over the place. Now, if we distribute the scene by base meshes, an object is actually the union of the respective base mesh and all its instances. With a configuration like this here, the object bounding boxes would be huge. Remember how, when we sweep our split plane, we align the candidates at the object bounds? Now you can see how that would be a problem here. That problem would be similar with binning. Now let's assume that we also have one huge, single instance base mesh like this one here. Imagine it's some type of terrain model, which is pretty common for the scenes we deal with. Now that messes up everything. No matter how we partition, if by base mesh or by instance, this type of base mesh would need to be replicated on all compute nodes in any case. That's a huge problem if the base mesh is very complex. Let's have a look at this part of the Moana scene, namely the smaller mountain structure that is located near the beach. This part of the model nicely exhibits all those properties that pose the most challenges with this type of dataset. Here's that same model, but with random colors assigned by instance ID. And this here is only the base meshes. That is, we deleted all the instances and kept only the very first one we encountered in the dataset for that base mesh. What you immediately see is that the model is dominated by one huge terrain base mesh. Also, you can see that all the tiny bushes here are really just a single one that is spread out all over the terrain mesh. And I also want to direct your attention to this large tree here, which is instanced twice, which actually has a fairly complex geometry and high memory consumption. Here's that same image again, but now with all the instances visible. The colors now encode the base mesh IDs, that is, all the instances that share a base mesh now have the same color. Also note that there are now two of those huge trees. The decision we made is to distribute instances instead of base meshes. There are for sure approaches to also make base mesh distribution a bit more efficient. We consider instance distribution a more obvious choice, and the possible solutions to the various challenges to be more straightforward. When partitioning instances, the problem we have to take care of the most is base mesh replication. which will have an adverse effect on memory consumption. There are different types of heuristics that can be used to assess a possible split plane candidate. Middle split, for example, will just position the split plane in the spatial center of the domain. Median split will try to distribute as many primitives to the left as to the right side, and the surface area heuristic will try to minimize the combined surface area of primitives and bounding boxes and will therefore use a cost function. Median split, at first sight, might seem like a reasonable choice to balance memory, as it will distribute the same number of instances to both sides. When performing a median split over the instances, this will, however, not consider base mesh replication, nor will it take into account that certain base meshes will be overly complex and consume much more memory than other base meshes. Also note that the distributions we aim to find are not restricted to ray tracing algorithms. We, for example, assume that a parallel ray tracer will take the instances that are assigned to a compute node and will construct an optimal acceleration data structure, like for example a surface area BVH, on the node level. But the spatial partitionings that we find are not restricted to ray tracing, but might as well work with a distributed software rasterizer or with an OpenGL application. In order to control the base mesh replication problem, we propose two more heuristics that are evaluated for each split candidate. The minimal replication split heuristic finds a split by minimizing the number of primitives from underlying base meshes that we might replicate across the nodes. This minimal replication split can be achieved by considering a split through the instances, distributing the base meshes accordingly, and summing up the number of primitives from base meshes on each side of the split plane. We divide this sum by twice the number of primitives from base meshes contained inside the domain to obtain a value between 0 and 1. The reason for this will be explained later. Note that count left and count right in sum might be greater than the number of primitives inside the domain. This is because split planes straddling base meshes are potentially replicated. Considering twice the number of primitives inside the domain gives us a conservative upper bound for normalization. The best split candidate is the one where this metric is minimal. What is important to note is that although considering only base mesh properties, the split candidates are still determined by iterating over the instances. The next heuristic that we propose is the equal geometry split heuristic. This heuristic is relatively analogous to a median split, only that the split is again driven by the instances, while the costs of the split are computed based on their base meshes. We again find all the base meshes and count the number of primitives on the left and on the right. But with this heuristic, the optimal split will be the one where the absolute difference between the primitive count on the right and on the left is minimal. That way, the primitive count from base meshes will be relatively balanced. This makes sense, as on a distributed memory system, we want to distribute about the same number of primitives to each compute node. We again normalize this metric and determine its minimum. In isolation, neither of these heuristics will, however, be very useful. This, for example, is the outcome of the minimal replication split heuristic that will try to minimize the overall memory consumption from base meshes. Colors encode compute node IDs. Red indicates that instances straddle the optimal split plane and are thus assigned to more than one node. For better visual reference, we used the color gray from the terrain mesh. The optimal split with the minimal split heuristic will be the one where the base meshes are distributed to few or only a single node, as then we don't need to replicate base meshes at all. This here is the outcome of the equal geometry split heuristic run in isolation. One can see how the heuristic achieves this relative balance in primitive count, in this case here by the way primitives are triangles, by distributing the two huge trees in the middle to compute nodes with relatively few bushes. Note, however, that this heuristic distributes both of the huge trees to more than one compute node, which will result in high overall memory consumption. For reference, this here is a median split over the instances. And that's a middle split. Note how both of these fall short in finding good distributions with respect to memory consumption. We therefore propose to use a linear combination of the four heuristics as a combined heuristic for spatial splits in the presence of instances. This heuristic is quite effective. Note, for example, how the combined heuristic is the only one that finds a well-distributed layout where both of the two huge trees are assigned to one node. We decided to combine our two new heuristics with the median split heuristic, as that one, like the equal geometry split heuristic, is concerned with balancing entities on both sides. Only with median split, those entities are instances and not primitives or triangles. For models that are very heavy on instances, so that instances actually impact memory consumption, median split can help to further balance the distribution in that regard. We also combine our heuristic with middle split to find a partitioning that is well distributed in space to some extent. In general, a linear combination with all sorts of heuristics would be conceivable, as would for example be a combination with the surface area heuristic. In order to make our combined heuristic more accessible, we propose a formulation as a cost function with weights for each of the individual heuristics. This is where we normalized the two new heuristics in the first place, because that way it is easier to combine them. Note that we also normalize the outcome of the median and middle split heuristics by dividing by the size of the combined object bounds in the split direction. For this example, and for all the results presented in this talk, we assigned the value 1 for each of the weights but W1, which is the weight associated with the minimal replication split heuristic. For that weight we assign, without loss of generality, the value 5, to emphasize our objective to keep overall memory consumption low. Now that we have our split heuristic in place, we only need to define a halting criterion to determine when the construction algorithm should return from the recursion. As we want to find assignments of objects to compute nodes, we already know the number of leaf nodes of the KD tree as just being the number of compute nodes. So we can just build a balanced tree and stop the recursion when the desired number of leaf nodes is reached. Note that one reason for KD trees being relatively unpopular for ray tracing is that the number of KD tree leaf nodes is not known a priori when we use the KD tree as an acceleration data structure. That is in contrast to a BVH, where we usually know that the number of leaf nodes is proportional to the number of objects. Obviously, this preconception doesn't apply in our case, as we know the number of leaf nodes to be the number of compute nodes. Now the only thing left for us to deal with is those huge single-instance base meshes. Those are still a problem, as they'll dominate the split decision. Before, we said that it is infeasible to reach into the instances and actually consider primitives or triangles when evaluating split candidates. For the large single-instance base meshes, we make an exception to that, but we still don't redistribute primitives all the time. Rather than that, we use a preprocessing step to quickly obtain virtual instances that we would obtain from actually splitting the base meshes. For that, let us consider what we actually need to know about an instance that we would like to insert into a KD tree. The only things we really need to know is an axis-aligned bounding box, and, for our two new heuristics, the triangle count from the base meshes that the instances refer to. For that, we only pretend that we actually split the base mesh, thus the name virtual instances, by using an auxiliary data structure to query the bounding box and the triangle count. Only when the KD tree is fully built up, we actually split the large base meshes at the domain bounds of the now fully created leaf nodes to obtain smaller base meshes that we distribute to the compute nodes. Therefore, we first identify all the large single-instance base meshes and projected triangle vertices on a uniform grid. At the grid cells, we store the number of triangle vertices. Note how each shared vertex is counted as many times as there are triangles that share this vertex. Now from this grid, we build up a three-dimensional summed area table. This will effectively discretize the domain of the base meshes. The resolution we used for the results in our paper is 256 cubed. From the summed area table, we can get both the bounding box as well as the vertex count inside the bounding box, which we use as an estimate for the triangle count. This can be done by using a simple shrinking algorithm, where the bounds of a conservative bounding box are tightened until the vertex count inside drops. So now, would we shrink the bounds a bit more, we'd have fewer vertices than were inside the conservative bounds, and as that would be illegal, we just stop here. Note how the bounds will sometimes be a bit tighter than the actual bounds of the triangles inside. This is because we only project the vertices to the grid, and by that throw away the triangle edges. That's not a problem though, as we only use the bounding boxes to steer a split plane heuristic, but never to actually distribute any triangles or to clip the main bounds against. And as we are equally likely to underestimate the bounds on both sides of the split plane, on average, this shouldn't make much of a difference for the decision where to place the split plane. To evaluate our data structure, we test our implementation with a couple of freely available landscape datasets. The PBRT EcoSys dataset is also used in the physically based rendering book by Farr and Humphreys and is hosted online by the authors. This dataset has 141 base meshes, 1.17 million triangles, and 12.8 thousand instances. The PBRT landscape scene can be found in that same repository and has 3,870 base meshes, 27.7 million triangles, and 408,000 instances. The Moana Mountain is a substructure of the Moana Island scene and consists of about 1,000 base meshes, 7.65 million triangles, and 2.3 million instances. The Moana Island scene by Disney was published by Rasmus Tamstorff and Havel Pritchett from Walt Disney Animation Studios. It consists of 1.46 million base meshes, 141 million triangles, and 66.5 million instances. Let us first have a look at how the distributions our partitioning algorithm generates will look like in comparison to middle and median split. Even from this informal inspection, we see already that our combined heuristic provides relatively balanced partitionings, and for example, that most of the bushes covering the Moana Mountain are assigned to a single node. We then analyzed the total memory consumption of the partitionings for different node counts with our algorithm and found that it is superior to the two simpler heuristics. The memory range that we report on the right is a measure for how balanced the distributions are across compute nodes, and our approach is also superior in this regard. Especially, we found that for certain models, the total memory consumption would sometimes grow uncontrollably with the other two heuristics. And only with our combined heuristic it was possible to get this behavior under control. It is also interesting to see how memory consumption varies when adjusting the various weights. So we conducted a sensitivity analysis by fixing all but one weight to the value 1, and then varying the value of that singled out weight. We again report results for the total memory consumption as well as the memory range. In general, we can see that the weights behave as expected under variation. We have integrated our partitioner into an MPI parallel and multi-GPU distributed path tracer. That path tracer uses wavefronts to distribute array workloads across compute nodes and implements naive forward path tracing with an omnidirectional light source. A good indicator of the effect of the partitioning scheme on the rendering performance is the number of rays that individual compute nodes exchange when rendering frames. We show heat maps generated with this path tracer that highlights regions where an excessive amount of ray transfers can be observed. We can see that although our partitioning algorithm is not specifically designed for rendering performance, that there is no excessive ray transfer across nodes. Our partitioning scheme that emphasizes total memory consumption is often even superior to the other heuristics. Finally, we report construction times our partitioner needs to build KD trees for the various datasets. We report those numbers for distributions to 32 compute nodes. Note that we use binning with 64 bins, a setting which of course has a huge influence on the construction performance. We also report the time to build up the summed area table for single instance space meshes. Also, we later split those space meshes into individual instances that contain only a part of the original triangles when the final partitioning was found. We also report results for that. So in conclusion, we presented a top-down KD tree construction algorithm to distribute large instanced 3D models to a fixed number of compute nodes. In the presence of instancing, this is particularly challenging because of large single-instance base meshes and because instances are often spread out all over the place. We tackle that by using a dedicated split heuristic and also by virtually splitting large base meshes using summed area tables. Our approach is based on spatial splits over the instances. Both object partitioning and partitioning over base meshes may be using early split clipping.
And you can unmute
Viable
yourself,
alternatives
Kurt and Stefan, right?
will be
In
interesting
Zoom
to compare with.
when it's time.
And with that, I wish to thank you, and I'm happy to take your questions.
For Q&A.
Hello there, Dan. Any questions from the audience? There's nothing on Discord. So I'll ask a question, Stefan. First of all, thank you very much for your presentation. I really enjoyed seeing the animations. A great piece of work. With these sort of ray tracing applications, you normally have the issue where you have a lot of coherence in the primary rays, but then they start splitting as secondary rays start bouncing around. So how do you see that as how do you tackle that in your method? Is this a possible issue as the number of bounces increases?
Yes, you have seen at one of my slides that we integrated this into a wavefront path tracer. So this is what makes sense. Distribute arrays in wavefronts are then compact rays. So you only use those rays that are active. And yeah, I mean, in general, this doesn't have to do with the partitioning scheme that we use. So the partitioning scheme doesn't aid in that, but we checked that there is no excessive ray transfer between the different nodes. But in general, the approach that you take is using a wavefront path tracer.
Excellent, thanks for that. Because we are a bit pressed for time and there are no more questions, we're going to move on a little bit, but please feel free, everyone, to keep asking questions in the Discord, and I'm sure the presenters will be very happy to take any questions there and answer them there if their Q&A session would have been over. Since we had a problem with the sound earlier, Stefan Freys, the Symposium chair, is going to present the introductory slides for the Symposium again.
Okay, good morning, everybody. I hope you can hear me now. Everything fine? Okay. So, first of all, I want to apologize for the technical difficulties we had. Apparently, we also had audio issues earlier, so please allow me to talk you through the opening again. My name is Stefan, and on behalf of my co-chairs, Gian and Philip, as well as our student chair Mo, it is my pleasure to welcome you to this year's Eurographics Symposium on Parallel Graphics and Visualization, EGPGV. So the mission of EGPGV is to provide a platform for exchanging experiences and knowledge regarding new methods and trends in parallel graphics and visualization. This is of growing importance due to various computationally demanding and data-intensive applications, both in graphics and in visualization. This necessitates the efficient usage of parallel hardware that has increasing complexity, like multi-core CPUs, GPUs, and cluster systems. Accordingly, EGPGV seeks papers on graphics and visualization that involve any type of parallel computing or focus on large data sets. This is the program that we have today with 2 sessions in the morning and 2 sessions in the afternoon. We're already in the middle of the first session in the morning that concerns itself mostly with graphics featuring 3 full papers. The second session this morning focuses more on visualization. It also has 3 full paper presentations. In the afternoon, we then have 2 short paper presentations as well as a panel discussion. And in the last session 4, we'll then have an exciting keynote on in situ data analytics given by Michaela Taufer. Quick note regarding our submission statistics. So we had 16 submissions in total and 8 accepts. So this gives us an acceptance rate of exactly 50%. As you know, additional to our regular deadline in March, we also had an early deadline in November where we received 2 papers, both of which we were able to eventually accept. Overall, we had a little fewer submissions than in the previous 2 years. On the left, you can see our great program committee who are responsible for selecting the papers, and on the right is our steering committee that is responsible for keeping EGPGV on track throughout the years. Finally, I want to thank the authors a lot for submitting to EGPGV, the IPC again for their great service, and of course everyone, you who tuned in for attending. I hope everything will go smoothly for the rest of the day. Now, without further ado, let's jump back into our technical program and EGPGV 2020.
Excellent. Thank you, Stefan, for that. Moving on to our next presentation. The paper is called Fast Multi-View Rendering for Real-Time Applications. The presenter is Johannes Guggenberger, and his co-authors are Bernard Kerbel, Markus Steinberg, Dieter Schmonstig, and Michael Wimmer. Johannes, Bernard, and Markus are Johannes, Bernard, and Michael are from the Technical University of Vienna University of Technology, and Markus and Dieter are from Graz University of Technology. This is another recorded presentation and should be streaming now, hopefully.
Hi, I'm Stefan, and today I'm giving this talk about finding efficient spatial distributions for massively instanced 3D models. Instancing is a technique that is used to get the memory footprint of large 3D models under control. The basic idea is to store a somewhat complicated mesh only.
Welcome to the presentation of the paper Fast Multi-View Rendering for Real-Time Applications. My name is Johannes Guggenberger from TU Wien. It is pretty obvious that we need to render multiple views for virtual reality applications. We need a separate view for each eye, or maybe even more views depending on the particular VR headset used. But there are also use cases for even more views, like visibility algorithms. Maybe to create a potentially visible set of primitives based on multiple ID buffers, each one of them produced by rendering one view. Another use case can be the creation of multiple shadow maps for different light sources. But how do you program the rendering of multiple views in a real-time application? There are many ways to do it, and different methods have been suggested in previous work, especially for stereo rendering. Yet it is unclear how these different approaches perform for different usage scenarios and if they scale nicely on current GPUs. The most straightforward way to implement it would be to just invoke a given graphics pipeline n times, once per view. We call this approach multipass. To render one view, we just activate the first frame buffer. Set the view matrix for the first view, which will be used in the vertex shader to transform the geometry for view 1, and issue the draw calls. The first view will be rendered. Actually, There can, or in most cases will, be multiple draw calls to render a scene. In all of my following slides, I will not refer to this again, but all the diagrams I am going to show you have this loop going from 1 to D, which shall indicate that multiple draw calls can actually be needed for drawing the result of one view. In an actual application, this would behave about like the following animation illustrates. After rendering of one view has completed, we perform all these steps all over again. Another frame buffer is activated. The next view matrix is set, and the draw calls for view 2 are issued. This is repeated n times until all the views have been rendered. We describe such a pipeline with the pipeline notation that is displayed at the bottom right. The last parameter of the pipeline function refers to the frame buffers. It means that all of them are separate in this case. The arrow, the middle parameter, refers to the way how geometry is processed throughout the pipeline. In this case, geometry is just moving straight through the pipeline, so to say, requiring only vertex and fragment shaders. The first parameter, the n, refers to the number of pipeline invocations with respect to the number of views. In this case, we have to issue all our draw calls n times, once per view. This multipass approach seems like a very naive and brute force approach, but already here we have some possibilities for variations. We can use a single big partitioned frame buffer instead of separate frame buffers. Since we only have one frame buffer, it only has to be activated once. But we must loop n times also for this pipeline variant. Instead of setting a different frame buffer for each view, we are setting a different viewport in the same frame buffer. Issuing the draw calls for the current views renders only into that viewport. The pipeline description function for this variant has the following parts. N as the first parameter, meaning that all draw calls have to be issued n times, once per view again. The way geometry is passing through the pipeline stays the same. And for the third parameter, we are specifying that the big partitioned frame buffer is going to be used. In addition, we must use clipping to restrict rendering to a certain region of it, indicated by the fourth parameter. Now, does a different frame buffer format already make a difference? Let's compare the frame times of those two approaches by just calculating the relative frame times. Subtracting the milliseconds of the approach with the separate frame buffers from the milliseconds of the second approach, the one with the big partitioned frame buffer. This yields the following results. Depending on the graphics card used, one or the other method is slightly faster. Results below the line at 0 milliseconds indicate that the variant with the big partitioned frame buffer has been faster, while results above the line indicate that the variant with separate frame buffers has been faster. The results vary a bit depending on the GPU, but for many of the GPUs, the results lie just within 0.5 milliseconds. Therefore, we cannot really recognize a clear winner in this competition. All the results that I am showing you here on this slide, and also in the following slides until we get to the last chapter of this talk, are based on measurements of ID buffer generation. Every view that is produced contains just the primitive IDs of rendered triangles. We chose this as the basis for our evaluations because ID buffer generation has little vertex shader and fragment shader load, which enables us to focus on the pure pipeline characteristics. And additionally, the view thruster overlap, so the potential for optimizations of certain pipeline variants is maintained because geometry can be shared across views. Speaking of geometry, that brings me to the second chapter, where we are investigating how geometry is processed by a graphics pipeline. Or in other words, let's take a look at the journey of the triangles through different variants of graphics pipelines. In the case of our multipass pipelines, the journey of the triangles is straightforward, in every loop iteration and for every draw call. Triangles are just moving straight through the pipeline, which only has a vertex and fragment shader. One triangle remains one triangle throughout the pipeline and eventually is being rasterized into the active frame buffer region if it does not get culled before that. So the point here is that the loop to produce all n views is on the CPU side. Using different pipeline variants, this loop can be transferred into a GPU loop, namely into a geometry shader. All view matrices are loaded into a buffer and can be accessed from the geometry shader. Triangles are only submitted once for all view matrices. And the geometry amplification happens within the geometry shader, and triangles are created from one input triangle, one for each view. Each one of these triangles is transformed individually and rasterized into a different frame buffer layer. Please note that in the animation only 3 frame buffer layers are highlighted exemplarily for all n layers. Actually, when rendering n views, all n layers would be rendered into simultaneously, but the animation shows only 3. Let's look at the animation once again for multiple triangles. The pipeline function which we use to describe such a pipeline is the following. Its first parameter is 1, because the draw calls are only issued once for all n views. The second parameter indicates that geometry is amplified using a loop in the geometry shader. And the third parameter refers to the frame buffer layout, which is a layered frame buffer in this case with n layers. There is another variant which is geometry shader based and works very similar to this. However, it does not require a loop in the geometry shader, but instead uses a feature called geometry shader instancing. Again, while the previously introduced variant uses a loop in the geometry shader and iterates through all the view matrices using that loop, the geometry shader instancing based method gets its geometry shader invoked n times, each time with a different instance ID which can be used to get the right view matrix. Do these geometry shader based variants perform better than the simple multipass approach? Millisecond differences below the 0 milliseconds line indicate that the geometry shader instancing based pipeline is performing better than multipass. Millisecond differences above the 0 line indicate the opposite. Multipass has been faster than geometry shader instancing. These box plots show the accumulated data from all test cases, which also include tests with different numbers of views. The more views are produced, the slower the geometry shader based methods get. This is actually not what we expected, is it? Anyways, we clearly need something else. But before we take a look at other options, I would like to shift from comparisons in milliseconds to comparisons in percent. What has changed is the representation. Multipass is used as the baseline, and the performance of the geometry shader instancing based technique is measured in percent of the baseline. That means in percent of multipass performance. And now, which different configurations have we measured? We have performed complete measurements on 6 different GPUs. We've measured on different generations of NVIDIA GPUs, including Maxwell, Pascal, and Turing microarchitectures. We have performed the measurements in 6 different scenes. We took smaller scenes like the well-known Sponza, and also larger scenes like the Amazon Bistro or the San Miguel scene. The scenes were tested in different geometry representations, which concretely means finer or more coarsely subdivided. We have applied CPU-based view frustum culling in order to create realistic usage circumstances. The degree of scene subdivision leads to varying numbers of draw calls per view position, or per set of view positions for those pipeline variants that only require all draw calls to be submitted once in order to produce all n views. All tests were performed in 4 different view configurations: stereo rendering, 4 matrices, a 4x4 grid yielding 16 different view positions, and also a 8x4 grid yielding 32 different view positions. Furthermore, all measurements have been performed in different resolutions. We have simulated additional vertex shader load to test what happens if an application requires demanding vertex shaders. To simulate increased fragment shader load, we have performed tests with G-buffer rendering. And finally, we tested the influence of overlap between the view frustum. But before we take a deeper look at the measurements, we still need fast techniques. A few years ago, an extension has been proposed and implemented by many GPU vendors. In the OpenGL world, its name is OVR Multiview, and it offers hardware-accelerated rendering of multiple views. That is, exactly what we are looking for. Let's see how a pipeline diagram of hardware-accelerated multiview would look like, but first, let's remember what geometry shader instancing looked like. The key point here is, where the geometry amplification happens, in the geometry shader. Now let's switch to hardware-accelerated multiview. The view matrices need to be consumed in the vertex shader instead of in a geometry shader, and geometry amplification happens somewhere before the vertex shader. This is indicated with the dashed circle containing a question mark. It is a question mark because we do not know exactly how geometry is amplified, since its implementation is vendor-specific. We describe hardware-accelerated multiview with the following pipeline function. There is only one invocation of all the draw calls. Geometry amplification happens probably somewhere before the vertex shader. In terms of usage, we definitely get multiple invocations of vertex shaders, each with a different view ID. We use this view ID to transform a vertex with respect to the corresponding view. The frame buffer layout is one single layered frame buffer with n layers. Let's watch the journey of the triangles for this case. After geometry has been amplified by the hardware extension, it is rendered into all n views in parallel. Also here I have just animated 3 different target layers, but please imagine that all n layers are rendered into in parallel, one for each of the n views. Let's watch the animation of this hardware-accelerated multi-view again. And then let's see if that finally brings some performance improvement over multipass. First of all, we only have NVIDIA GPUs left in the diagram, because AMD does not support hardware-accelerated multi-view. Secondly, we can finally see some good performance. The median of the 2 high-end Turing GPUs indicates that using the OVR multi-view extension takes approximately 25% less time to render a scene compared to multipass. However, on other GPUs the performance numbers are still not better than multipass. Shouldn't that be the fastest possible way? We need to take a closer look on hardware-accelerated multi-view rendering. The question is, how many views can actually be fully hardware-accelerated? The Pascal white paper says, with Pascal's SMP engine, which supports 2 separate projection centers, the GPU can render the 2 stereo projections directly in a single rendering pass. And the Turing white paper says, Turing hardware supports up to 4 views per pass, and up to 32 views are supported at the API level. So on Pascal 2 views can be rendered with full hardware acceleration, and on Turing 4 views can be rendered with full hardware acceleration. But 32 views are supported on the API level. Shouldn't the API schedule rendering of more than 4 views in the most optimal manner? We have to check. We are testing what happens if we only produce 2 views at a time, but fully hardware accelerated on Pascal. And on Turing, we would always produce 4 views at a time, also fully utilizing hardware acceleration. This has the effect that we increase loop iterations once again to n over 2 on Pascal and to n over 4 on Turing. Let's look at the adapted pipeline diagram. Here we see the return of multiple iterations. N over 4 iterations in this example in order to produce n views, each of which is rendered into a frame buffer with 4 layers, one for each hardware accelerated view. Next iteration, next frame buffer. And so many iterations until all n views have been rendered into n over 4 frame buffers. In the vertex shader, we just have to make sure to get the right view matrix. But other than that, the rest is just the same as with the other OVR multi-view pipeline variant. The differences are that we have more iterations are rendering fewer views, but all of them fully hardware accelerated. Back to the performance comparisons. This is the same diagram that I've shown before making the adaptations to the OVR multi-view pipelines. Let's now switch to the new, fully hardware accelerated variants with more iterations. Oh, that looks better. Performance is better than multipass in most of the cases on all GPUs. On NVIDIA's high-end Turing GPUs, actually in virtually all cases. I would now like to define those fully hardware accelerated variants as the new baseline for further diagrams. This slide shows different other pipeline variants with the performance compared to fully hardware accelerated multi-view. Let's go through the pipelines one by one. First one is our well-known multipass. In the second column, you can see the second multipass variant, the one which uses a big partitioned frame buffer. In the third column, we have an optimized version of the geometry shader amplification variant Column 4 shows an optimized version of the geometry shader instancing variant. In column 5, we can see the original version of hardware-accelerated multiview that makes use of the graphics API in order to render up to 32 views with one single pass for all n views. The last two columns show further optimized geometry shader-based variants. What kind of optimizations are those? Let's see. To start, let us take another look back at our initial variant of geometry shader instancing. There is only one pass to produce all n views. During our investigations, we were able to find out that also switching these variants to versions that do only produce 4 views in one pass and increasing the number of passes accordingly leads to significant performance increases. This version needs to submit all draw calls n/4 times as often as the version with only one draw call. But this leads to better work distribution on the GPU and finally to a significantly increased performance despite the higher number of draw calls. n/4 iterations are required to produce all n views. Each batch of up to 4 views is rendered in a separate frame buffer. Furthermore, we discovered that adding custom viewfrustum culling and backface culling to the geometry shader increased performance even more. Culling reduces the amount of work that has to be processed in the geometry shader and in subsequent stages of a graphics pipeline. The two geometry shader-based pipeline variants that utilize all of the optimizations presented in the previous slides are those in the two rightmost columns of the diagram. Fully hardware-accelerated multiview seems to be faster in almost all cases, but there is an interesting region that is definitely worth being further investigated. There are some cases where our shiny new optimized pipeline variants are able to outperform hardware-accelerated multiview. Let's finally look at the performance trends that we were able to spot during our evaluation of the results. Which are the cases where the optimized geometry shader variants are faster? Since our focus is on them for now, I'll scale the arrows to the quartiles of the geometry shader instancing variant. Let us investigate how the results change when we only take the test cases into account that produced 16 or 32 views, and additionally, let us restrict the data to the larger test scenes like Bistro and San Miguel. That is good news for our geometry shader variants. They are showing better performance than the fully hardware-accelerated pipelines in the majority of test cases. On the contrary, this means that they are probably not doing too well with few views, referring to our test cases with 2 or 4 views. Also, for smaller test scenes the results can look different. What we found out is that for smaller scenes, the pipeline performances move closer together. That actually means the larger scenes are more interesting to analyze because they probably point out performance characteristics better. Remember, however, these diagrams are generated across all NVIDIA GPUs, so there can still be huge differences across the different hardware generations. Let's see what happens on Turing microarchitecture GPUs. Okay, fully hardware-accelerated multiview rendering is coping particularly well on Turing. All other pipeline variants lose performance compared to it. However, there is still a bright spot with respect to the convert pipelines here. The optimized geometry shader instancing variant has its median value pretty much exactly at the 100% value. Overall, we can say that for producing many views in large scenes, geometry shader instancing is able to show very competitive performance even on the Turing microarchitecture. That is, as pointed out, only on Turing, the performance of optimized geometry shader instancing becomes even better on older microarchitectures of the Maxwell and Pascal generations. Let's see. Now these are some very cool results. Both of our optimized geometry shader variants strictly outperform hardware-accelerated multiview rendering on older NVIDIA microarchitectures for many views in large scenes, taking only about 70% of the rendering time to produce all the views. Not only on older generations we could observe good performance, but also generally on lower tier NVIDIA GPUs. Let us restrict the results to the two low tier GPUs that participated in our tests. And also in this case, we can see that the two geometry shader based variants outperform fully hardware accelerated multiview in virtually all test cases with many views in large scenes. Let us investigate some more parameters. What happens if we increase the vertex shader load drastically? we can observe that performance numbers shift a bit in favor of fully hardware-accelerated multiview, but our geometry shader-based variants are still showing good performance. Interestingly, if you pay attention to columns 3 and 4, the purple and blue one, it is obvious that the geometry shader-based variants, which require only one pass of draw calls to produce all n views, catch up in terms of performance. This is expected, however, because fewer vertex shader invocations happen in these cases. The geometry is multiplied after the vertex shader, in a geometry shader loop or by the means of geometry shader instancing. Let us remove the filter to the low-tier GPUs and take a look at the complete picture across all GPUs once again. The general trend that performance shifts in favor of fully hardware-accelerated multiview is noticeable, but in these cases, geometry shader-based variants with only one pass of draw calls generally perform better. The message here is that if you know your specific use case, you can make informed decisions about choosing the right pipeline variant. We have looked at increased vertex shader load. Now let's take a look at what happens with increased fragment shader load. The performance numbers here are based on our test cases from gbuffer rendering. Fully hardware-accelerated multiview is able to gain ground with respect to all other pipeline variants. We attribute this to the shading cache, which is a feature of NVIDIA's hardware extension. Increased fragment shader load does not have such a huge impact on performance when using the hardware extension, while other pipeline variants do not use any cache and suffer the full impact of increased fragment shader load. Before I come to the end of my presentation, let us investigate one more interesting case, the effects of viewport discrepancy. All test results that we have looked at so far are from test cases depicted on the left-hand side on this slide. All views are close to each other, and the overlap of geometry rendered from the different views is generally rather big. Views are only slightly offset from each other and always look in the same direction. There are other use cases where there is only little or maybe no overlap at all. This use case is illustrated on the right-hand slide. Imagine, for instance, producing shadow maps for multiple spotlights distributed across a scene. The view thruster of these spotlights might not overlap, or maybe overlap only a little bit. How does such a scenario impact performance of multiview rendering? Quite severely, as it turns out. While our optimized geometry shader-based variants show similar performance to fully hardware-accelerated multiview, all of them are quite heavily outperformed by simple multipass, the naive, quote-unquote, techniques from the very beginning of this presentation. They only require 60% of the rendering time of fully hardware-accelerated multiview, often even less. For incoherent view thruster, the geometry cache of hardware-accelerated multiview becomes a burden. Also in the case of geometry shader-based techniques, our optimizations that cull geometry are not effective anymore, and the geometry output overhead per input primitive has a negative impact on performance. All in all, we recommend simple multipass for incoherent view thruster based on our empirical data. Let us change the baseline once again to multipass in this case. It can be seen that other pipeline variants take generally 150% of multipass rendering time or much more, which is a very significant difference. And, by the way, this is what performance on our AMD GPUs looked like all along for all of our test cases. Multipass outperforms every other pipeline variant in any test case on AMD. With this, I would like to conclude my talk, where we have investigated different variants of graphics pipelines. We have examined the journey of triangles throughout different pipelines and especially focused on where the geometry is amplified. We have seen hardware support for accelerated multiview rendering. We saw how geometry shader-based variants can be optimized so that they reach competitive performance compared to hardware-accelerated multiview in many cases, while still offering full support for custom tessellation and geometry shaders. And we have looked through the performance trends of several selected test cases. I would like to thank you for your attention during the presentation of fast multiview rendering for real-time applications.
Yes. Thank you for that, Johannes. Another excellent presentation. It was great to see all those animations again, so lots of results also. I have a question from Andreas Basilakis. He's asking, what's the API that you have used to implement these multi-view rendering solutions?
We have used OpenGL because that enabled us to better analyze the performance exactly on GPUs. Because with tools like NVIDIA Nsight, they offer more features for analyzing OpenGL pipelines than Vulkan pipeline, for example. So we considered using Vulkan, but in the end, we just implemented it in OpenGL. And actually, we do not have a lot of CPU work to do where the Vulkan API would potentially have benefits in terms of performance. So the work is mainly done on the GPU, so OpenGL should not distort the results, actually.
My follow-up question is whether you've tested on any mobile devices.
No, we haven't tested on mobile, but that would definitely be interesting.
Excellent. I'm going to leave it at there in terms of questions. So feel free, anyone watching on YouTube, to go to the Discord channel and ask any questions there, and keep asking questions even after the session is over. I'm sure the presenters will be happy to answer them. So we're going to be moving on to the next presentation, the final presentation of the session. This presentation is entitled Moment-Based Opacity Optimization. The presenter is Mahmoud Zaidan, and he's co-authored the paper with Tobias Rapp, Christoph Peters, and Carsten Dashbacher, all from Karlsruhe Institute of Technology. So this is another presentation which has been pre-recorded, and the presenter will be here for Q&A right after.
Hello and welcome everyone, and thanks for being here. Today I will present our work on moment-based opacity optimization. First, I would like to explain the motivation behind our work. So, opacity optimization is a visualization technique which is used to highlight important structures and reduces visual clutter within dense geometry. As you can see here, by using opacity optimization, we are able to see the internal vortex structure of the tornado dataset. In general, opacity optimization assigns opacity for rendered fragments in order to remove the foreground clutter and the background clutter around important structures. This brings us to the main contributions in our work. First, we present a novel approach for opacity optimization based on recent state-of-the-art moment-based techniques for signal reconstruction. Second, we present a fast screen space filtering approach for optimized opacities. And finally, we compare our technique to recent state-of-the-art techniques for opacity optimization on several datasets. Before I explain our technique, I would like to briefly discuss some of closely related work on opacity optimization. In the beginning, I would like to talk about decoupled opacity optimization. Decoupled opacity optimization is a least square minimization problem. Using the analytic solution of this problem, we can find the optimized opacity value for each rendered fragment along the view ray. Let me explain the optimization process in more detail. If we look at this figure and given a list of fragments along the view ray, each fragment is assigned an input importance value. This importance value ranges from 0 to 1 and represents how important a certain geometric segment in the overall context of data. Then, for each rendered fragment at certain depths, we can find the optimized opacity value using this formula. Since this formula represents the basis of our work, I will explain each term separately in the next few slides. The first term we want to highlight represents the accumulated squared importance up to certain fragment depths. This term is an important measure of the geometric structures in front of the current fragment. As shown in this figure, we display a simplified view of the accumulated importance of 4 rendered fragments. The next term we want to highlight is the total sum of squared importance along the view ray. By subtracting the accumulated importance up to certain depths from the total importance, we can have a representative measure of the geometric structures behind the current fragment. In this equation, we have 4 user control parameters. The first parameter is a regularization term, which is used for the optimization process to prevent empty rendering. The second parameter Let us emphasize important structures and put more focus on them. The third parameter is used to penalize background clutter. And the fourth parameter is used to penalize foreground clutter. An A buffer was an interesting way to solve decoupled opacity optimization problem in practice. With A buffer linked list, we store with each fragment its corresponding importance value. Then, this linked list is sorted from front to back, and in the final rendering pass, optimized opacity value is evaluated per each fragment in order. However, two main problems might arise with A buffer solution. First, since we build a linked list per each pixel, this might lead to unbounded memory requirements for moderate or large datasets. Second, sorting the linked list incurs additional overhead, which makes the technique in general slow. Now we come with another important step in decoupled opacity optimization. Once we optimize the opacity per pixel, it might lead to discontinuities in the opacity along adjacent vertices. Opacity optimization solution used to smooth the opacity values along geometric structures. In order to do that, first, input structures are divided into smaller geometric partitions. As we see here, a large line is divided into smaller line segments. Then, the optimal opacity is stored per line segment. And finally, a Laplacian smoothing kernel is applied to each line to smooth the opacity along longer segments. The object space filtering adds additional overhead to the decoupled opacity optimization technique. In the beginning, we have to divide input structures into smaller partitions and maintain adjacency information. Specifically, line is divided into line segments and the surface is divided into surface batches. And the filtering process has to handle lines and surfaces differently. Very recently, a Fourier-based approach has been used for opacity optimization. In this work, Baiza and colleagues replaced the accumulated importance along the view array by a Fourier series approximation. As shown in this figure, a Fourier series can be used to reconstruct accumulated importance along the view array. The Fourier opacity optimization technique has several advantages. First, it is memory bound, since we store few Fourier bands, in practice 4 to 5 bands, into render target buffers. By doing so, we get a big memory gain relative to the A buffer implementation, since we use a fixed number of screen space structures to store Fourier coefficients instead of using dynamic linked lists to store the importance. Second, we replace the complicated linked list sorting by order-independent Fourier signal reconstruction of accumulated importance along the view array. However, Fourier opacity optimization comes with several issues. First, using truncated Fourier series for discrete signal representation might produce visual artifacts. Second, with Fourier opacity optimization technique, we still have to perform object space filtering to smooth opacity values across adjacent segments. Before I talk about our moment-based approach for opacity optimization, I would like to talk about moment-based order-independent transparency technique presented in 2018. With moment-based order-independent transparency, moments has been used to compactly store absorbance signal along the view direction. And using a few number of moments, we are able to reconstruct original input signal in an efficient way. As shown in this figure, moment-based reconstruction has a better representation than the Fourier series of absorbance signal, and the reconstructed signal from moments does not suffer from the ringing artifacts produced from the Fourier series approximation. Moment-based order-independent transparency was proposed as an improvement of the Fourier opacity mapping for order-independent transparency. And since Fourier opacity optimization is based on Fourier opacity mapping, we expect that moment-based opacity optimization could be a viable improvement in the context of opacity optimization. As we see here in these two figures, we would like to highlight that both order-independent transparency and opacity optimization represents quite similar problems with two different signals and contexts. let me highlight why we would prefer moments rather than Fourier series for discrete signal representation and reconstruction. First, moment-based reconstruction of discrete signal has shown to be highly accurate for sparse regions and also feasible for densely covered regions. Second, as we see in these two figures, and in contrast to truncated Fourier series, moment-based reconstruction does not suffer from sphere ringing artifacts for large sparsely populated signals along the depth range. Well, let me talk in detail about our moment-based opacity optimization technique and explain our main contribution in the next few slides. In this diagram, we show the main processing steps of our moment-based opacity optimization approach. Generally speaking, we use a rendering path to accumulate the importance into moments buffers. Then we replace object space smoothing with screen space filtering of moments buffers. And finally, we substitute the optimized opacity value into the final compositing and rendering path. In the first step, we generate moments coefficients out of importance signal. So for a given pixel with n fragments, we construct m-ordered trigonometric moments out of importance and depth values using trigonometric moments generation function. We use additive blending to accumulate moments coefficients into render target buffers. In practice, we use screen size textures to store these coefficients. And since we are using 3 trigonometric moments in our implementation, we only need 7 float channels in total. Similar to moment-based order-independent transparency and for efficient reconstruction, we logarithmically warp the input depth range into a range of -1 to 1. For more details, please look into our paper. As a second main contribution of our work, we introduce a more general approach to smooth opacities along adjacent geometric fragments. Given that we store moments in separate texture channels, we apply a two-pass Gaussian blower to each moment individually. As shown in this figure, we apply a Gaussian kernel of with 21 pixels to the tornado rendering. The bottom row shows the zeros moment before and after screen space filtering. As we see with the tornado streamlines, our approach achieves the core goal of filtering in opacity optimization by fading out clutter that occlude important structures. Our filtering approach for optimized opacities offers several advantages than object space filtering introduced in previous work. In terms of processing, our approach is relatively simple and fast, since in practice we use screen filling quiz to linearly filter moments textures in a ping-pong fashion. And in terms of memory overhead, our approach uses additional number of texture channels as similar as the number of moments. Once we filtered moments buffers, we use moment-based reconstruction to approximate the accumulated importance for each rendered fragment. This step is not separate from the rendering step and can be integrated into normal rendering pipeline. The only added complexity is that we bind moment textures as texture units in the renderer, and the opacity value that comes from the optimization equation is substituted for fragment opacity during final compositing. Our opacity optimization method is compatible with any method for order and independent transparency. For final rendering and compositing, we favored moment-based order-independent transparency for the aforementioned reasons. For moment-based order-independent transparency rendering, we use two render passes. In the first pass, we construct the moments buffer of input transmittance, and in the second pass, we use additive blending to accumulate reconstructed transmittance out of the moments buffers. Now, let me introduce the results and evaluations of our opacity optimization technique. Our visualization framework uses OpenGL 4.4. All aspects are GPU accelerated. We use the rasterization pipeline for opacity optimization and rendering. We evaluate our technique on datasets of points, lines, and arbitrary triangle meshes. and we compare our moment-based opacity optimization approach against decoupled opacity optimization and Fourier opacity optimization. We used streamlines of several datasets to compare the visual quality and rendering time of our technique against decoupled opacity optimization and Fourier opacity optimization. In the leftmost image, we disabled opacity optimization and used a buffer for rendering to convey the correct shape of the input geometry and highlight clutter around important structures. For the second image, we used analytic opacity optimization with a buffer implementation and used a buffer for rendering. In this experiment, we enabled object space filtering. In the third image, we used Fourier opacity optimization with screen space filtering for opacity optimization and Fourier-based approach for order-independent transparency. And in the rightmost image, we used our moment-based technique with screen space filtering for opacity optimization and used moment-based order-independent transparency for rendering. In these settings, our approach provides quite similar results in terms of visual quality related to both decoupled opacity optimization and Fourier opacity optimization. In terms of running time, our technique has a relatively large gain in regard to decoupled opacity optimization and has quite similar running time relative to Fourier opacity optimization. The next dataset shows the magnetic field lines in the decay of magnetic knot. We show a close-up of two symmetric rings in this dataset, and opacity optimization helps us to discover this ring structure behind foreground clutter. The discriminant visual differences between decoupled opacity optimization at one side and Fourier opacity optimization and moment-based opacity optimization at the other side comes since we use different filtering techniques. As we use object space filtering with decoupled opacity optimization and we use screen space filtering with both moment-based opacity optimization and Fourier opacity optimization. However, as shown in the magnified insets, our filtering approach is still successful in smoothing opacity along neighbor structures and decaying foreground clutter in front of important structures. This dataset highlights the really benign convection that comes when a thin layer of fluid is heated from below. Opacity optimization achieves a good viability of the resulting convection cells and keeps lower flows when they don't occlude important structures. In this figure, we show a visual validation of correctness of our technique. For this experiment, we disabled object space filtering with decoupled opacity optimization and disabled screen space filtering with Fourier opacity optimization and moment-based opacity optimization. Please keep in mind, since we disabled object space filtering with decoupled opacity optimization, we optimize the opacity directly on fragment basis along the view ray. We used a buffer for final compositing in order to separate the error that comes from our solution for opacity optimization using moments. As we see here, the visual differences between the reference solution using decoupled opacity optimization is minimal against Fourier opacity optimization and moment-based opacity optimization. Using an error plot, we can admit that our technique has a slightly bigger error than Fourier opacity optimization, although it has little effect on the final visualization. The greatest errors occur in regions with important lines near unimportant lines and strong overdraw. However, Fourier opacity optimization uses 9 coefficients, whereas our technique uses only 7. In this figure, we highlight the use of screen space filtering to remove clutter. In this regard, we compare decoupled opacity optimization with object space filtering against moment-based opacity optimization with screen space filtering. Using 21 by 21 Gaussian kernel for screen space filtering, we achieve the core goal of filtering by smoothing opacities along neighbor and close geometric structures and fading out unimportant clutter that appear in front of important structures. In this figure, we use moment-based opacity optimization with points of tornado vector field. In this scenario, we use velocity as an importance measure. Opacity optimization helps us to detect the internal vortex core structure in this point dataset. This experiment demonstrates a nice use case of our skinny space filtering. We use two triangle meshes with complicated topology. Using object space filtering with the patch structure is not trivial in this situation, and would be difficult since this mesh is not designed with such requirement in mind. On the other hand, our skinny space filtering is trivially applicable without adding any spatial to the implementation. In this example, the bunny has much higher importance than the patch structure, and using opacity optimization with screen space filtering, we can discriminate the bunny behind the frontal leaf structures. In conclusion, we presented a novel approach for opacity optimization based on moments. Our technique is faster and easier than decoupled opacity optimization. The quality and the speed of our technique are similar to Fourier opacity optimization. We achieve a low memory footprint with our technique. The screen space filtering proposed with our approach decouples the implementation of opacity optimization from the geometric representation. For future work, we are interested in exploring automatic ways to find optimization parameters and extending our approach into large datasets on multiple GPUs. Thank you so much for your attention.
Thank you very much, Mahmoud. Another excellent presentation. So don't have any questions from the audience. I'll ask a quick question then. So you compare your results using some screen space error, is that correct?
Yeah, exactly, yeah. Sorry.
Yep. So how do you, is there any way of determining perceptually how big that error is? So if the error is small, does it really matter?
Yeah, I think so. I think maybe a way to do that is to examine specifically certain pixels into our experiment that we measured the error throughout the whole scene. So I think examining several pixels with different layers of geometric structures might be a nice way to measure that. Yeah, I think so. Yeah.
Excellent. Thank you for that.
Yeah.
Okay, we're going to stop here. Let me please thank the presenters once again, and my apologies for not having more questions for you, but we're quite tight on time since we started a little bit later. So it's been quite successful to have over 100 people watching on the YouTube channel throughout. So please join us in a little bit more than 10 minutes, okay? The technical team needs to set up the rest of the speakers. So we're meant to be starting at 11, but we'll probably be a few minutes late. So go grab yourself a hot drink or a cold drink if you prefer, and join us in about 10 minutes or so. Hope you enjoyed the rest of the conference.
Thank you so much.
Thanks.
Yeah, well done, everyone. Thanks a lot, Kurt, in particular for handling this so nicely, and for.
Well, I hope so. I always get nervous with these things. There's so much happening.
Yeah.
I have the computer set up just to make sure things are smooth, and it might not have been a good idea. It was a bit more confusing. Well done with the conference. It's interesting having it this way, but I think the advantage is the presentations are really good because they have time to prepare them and record them. And so there are some advantages of having it online, I guess. And a bigger audience than we normally have, having over 100 people. I don't think that's happened frequently at EGPGV.
I have strong feedback
Oh, sorry about that. I was just saying it's good to have so many people at EGPGV.
Yeah, thank you very much.
Right, I'll see you later, Stefan.
Yeah, see you later. Thanks
Bye.
again.
Bye for now.